So to summarize what we have learned so far in linear regression, which is an instance of supervised machine learning algorithms, we have a data set which is a set of m data points xj and yj, where j equals 1 to m. We have a feature mapping phi of x, which forms perhaps a nonlinear representation of the input data points x. We are using a linear model, where the function f that maps x to y's is some function of parameters, learnable parameters w, that takes in the phi of x and produces the target values as w transpose times phi of x. We are using the L2 norm squared as our loss function, and these are the matrices phi, and this is a vector y of target values. This is a matrix phi of the input feature points. This is an m by n matrix. The optimal solution, if we take the L2 square loss function, is W star, which denotes the optimal solution, is phi transpose times phi inverse times phi transpose times y. So this is a closed form solution for W, to derive the optimal W. It minimizes the loss function, the squared loss function, over the dataset for this linear model. So let's analyze what this solution represents, right? So to compute this solution in a closed form, we have this matrix phi, which is an m by n matrix, right? So first we have to multiply two m by n matrices, right? So phi transpose times phi. This matrix is now n cross m, and this is m cross n. Right. To write it again, like so, we can show it here. Phi transpose times phi. So this matrix is n by m, and this is m by n matrix. So the resultant matrix phi transpose phi is an n by n matrix, where n is the number of feature points, or n is the dimension of the basis functions or the feature function, right? So, and then we have to invert this n by n matrix. So if the input dimension is very high, or the feature function or the basis function's dimension is very high, then this, for example, let's suppose if n equals 10,000. In that case, this matrix would be a 10,000 cross 10,000 matrix, and then we'll have to invert a 10,000 by 10,000 matrix, right? And then we have to multiply it by phi transpose times y. And this can be a huge amount of computation. Even to multiply these matrices together is very computation intensive, and then to compute the inverse is going to be much more time consuming, and may not be practically feasible for problems that have very high dimension. For example, if n is close to like 10 to the power 5 or a million, right, then this matrix would be 10 to the power 6 cross 10 to the power 6. We wouldn't even have that much amount of RAM in our computer to actually store this matrix and then to compute its inverse, basically. So rather than computing this closed form solution, so this closed form solution is valid for smaller size problems, right? When m and n are typically smaller in size, and typically like when n is if n is under 1000, perhaps you can compute this inverse very reliably, and this can perhaps be done in real time with the modern computers. But for often for most problems, this may not be practically feasible. So that's why we need a better algorithm that can make use of the data and can compute this optimal solution W star in a much more efficient manner. And that's what we are going to teach you, like how to compute this solution, optimal solution W, in an online fashion. So the algorithm to do this is known as gradient descent. It's an online learning algorithm. So we are going to teach you an algorithm known as gradient descent.